I would argue that one of the most powerful tools in trigonometry are the trigonometric identities. They appear everywhere when you are trying to solve problems that require manipulation of the trig functions. But we're not going to be looking at any of these identities. We're going to be focusing on the Pythagorean identities. Let me lay them out for you. The first identity is sine squared x plus cosine squared x equals 1. The second, 1 plus tangent square x equals secant square x. And the final, 1 plus cotangent squared x is equal to cosecant squared x. The first time I saw these, I was very confused. The first identity has the sum of two trig ratios being squared equal to a constant, but the other two have a constant plus a ratio squared equaling another ratio. At first, this does seem like witchcraft, but I'm going to show you an amazing way to visualize these identities. Let's start off with the first identity. The first thing I'm going to do is draw a unit circle, which is a circle with a radius of 1 unit. Now, almost all of the concepts from trigonometry come from this unit circle. So now let's say I have some point P that is on the circumference of this unit circle. So this line segment extending from the center of the circle to point P is a radius. Since it's the radius, the length of this segment is going to be 1 unit, since that is quite the definition of a unit circle. The segment forms some angle theta with the horizontal x-axis, and the value of theta doesn't matter here. Point P can be anywhere on the unit circle, but the idea still remains. From here, let's drop a line from point P that is perpendicular to the x-axis. What we see here is a right triangle with the hypotenuse being 1 unit. The coordinates of point P is x, y, where we don't know the exact values of x and y. They're still arbitrary. You can think of this as, to get to point P, we have to move some x units horizontally and some y units vertically. The y value is the side opposite to theta, so we simply label it as so. The x value is the side adjacent to theta, and the last side is simply the hypotenuse of this right triangle. To find the y value of our coordinate, we have to use a ratio that connects the opposite side of the triangle to the hypotenuse. And this is the definition of the sine ratio. So we can define this as sine of theta is equal to the opposite side, y, over the hypotenuse, which is 1. Simplifying, we find that the y value is literally sine of theta. Repeating this process for the x value, we need some ratio that relates the adjacent side to the hypotenuse, and this trig ratio is cosine. So cosine of theta is equal to the adjacent side, x, over the hypotenuse, which is 1. What we find is that the x-coordinate is literally cosine of theta. This means the base of the right triangle is cosine of theta, and the vertical side is sine of theta. And this is true for all values of theta and the location of point P. Now we can use the Pythagorean theorem, which states that a right triangle with legs A and B and hypotenuse C satisfies the equation a squared plus b squared is equal to c squared. The two legs of this right triangle are sine of theta and cosine of theta. And summing the squares of these values must equal the hypotenuse squared. So sine squared theta plus cosine squared theta must equal 1. And this is the first identity. And from this, we can derive the other identities from this one. For the second identity, we can divide this first identity by cosine squared theta. Cosine squared theta over cosine squared theta is simply 1. And sine squared theta over cosine squared theta is defined as tangent squared theta. If you want to know the reason behind that one, be sure to check out my video on this topic. 1 divided by cosine squared is secant squared theta. So we get the identity of tangent squared theta plus 1 is equal to secant squared theta. Now, instead of dividing the first identity by cosine squared theta, let's divide by sine squared theta. Again, sine squared theta over sine squared theta is simply 1, and cosine squared theta over sine squared theta is the reciprocal of tangent squared. So this value right here is defined as cotangent squared theta. On the right-hand side, 1 over sine squared theta is defined as cosecant squared theta. And with that, we have 3 of our identities derived. But to me, this isn't too satisfying. We had such a beautiful way of deriving the first identity from the unit circle, but the other two just came from simple division. I want to know if there is another way of finding these two geometrically, and it turns out there is a way. Returning to our original diagram, I'm going to draw a line tangent to the circle at x equals 1. Now let's extend our original segment to be a line that intersects with our newly drawn tangent line. From here you can see that we have a bigger right triangle where the lines intersect at the point let's call T. The base of this triangle is 1, since the base is the radius. We now need to find the other leg of the right triangle, and at first this seems impossible. There is no clear defined way to pinpoint the value of this leg. But for now, let's move away from geometry and enter some algebra. This line is a function, and since it intersects with our tangent line at the point that represents the height of our triangle, we can use the equation of a line to determine what this point is. Let's write the equation of our line in y equals mx plus b form. The slope of the line is simply the rise over the run. So if we isolate our view to the origin point and point P, we can reason that to get from the origin to point P, we must rise sine of theta and run cosine of theta. So the slope of this line is sine of theta over cosine theta. And if you would look at that, it is equal to exactly tangent of theta. The y-intercept, since the line passes through the origin, is simply 0. So our final equation for the line is y is equal to tangent theta x. The coordinate of t must satisfy this equation, since it lies on the very same line. We know the x-coordinate of t to be 1, so we can plug this into our equation to find the y value. So we get y is equal to tangent theta times 1. And what we get is that the y value is tangent of theta. So the height of this bigger right triangle must therefore be tangent of theta. Now we have one more side to find. And this one comes very easily if you think about proportions and similarity. These two triangles are similar. We know this because they share the same angle theta, and they are both right triangles. So by angle-angle similarity, the ratio of their side lengths must be proportional. The values we are trying to find on the bigger triangle is the hypotenuse. So let's choose two parts, one part that is the hypotenuse, that we can set up in a proportion. For this example, I'm going to relate the hypotenuse of the triangle to the horizontal legs of both triangles. For the smaller triangle, let's set up the proportion of its hypotenuse to its horizontal leg. The value of the hypotenuse is 1, and its horizontal leg is cosine of theta. Moving on to the bigger triangle, the value of the hypotenuse, well, we don't know that yet. So let's let some value x be equal to the hypotenuse. The base of the bigger triangle is 1. So we get 1 over cosine theta is equal to x over 1. Simplifying, we get 1 over cosine theta is equal to x. And this is the reciprocal of cosine, which is secant itself. Therefore, the hypotenuse of the bigger triangle must be equal to secant theta. There is another way to derive this though, and it's through scaling vectors. But I'll leave that as an exercise for those who want it. But here's a little hint. Try to find a scale factor k that scales up the smaller vector to get the larger vector. And that scale factor is going to be your hypotenuse. Anyway, now that we have our three parts of the bigger triangle, we can use the Pythagorean theorem. So 1 squared plus tangent squared theta is equal to secant squared theta. And simplifying, we just get 1 plus tangent squared theta is equal to secant squared theta. And there it is. We proved this identity geometrically. For the last identity, I decided not to go through it in detail, since it follows the same principles as the previous derivation. The key change is that instead of drawing a tangent line at x equals 1, we draw a tangent line at y equals 1. And for those wanting a challenge, this is a great exercise. So if you want, try this out on your own. And that concludes the 3 Pythagorean identities. I want you to think about how we approached this problem. We had a formula that we didn't quite understand, and we used the unit circle to figure out the first identity. Then instead of going down the orthodox division method, we used the concepts of the other ratios to craft together a visual representation of the other two identities. It always feels satisfying, doesn't it? This is why I want to encourage you to figure out why something works, and not just know how to solve it. And with that being said, I'll see you guys in the next one.